What if everything we thought we knew about the beginning of the universe was missing crucial pieces of the story? Picture this: the moment of creation, the birth of time and space, the fiery dawn of existence itself. It's a tale we've all heard in fragments, but hidden beneath the surface are mysteries, twists, and forgotten truths that could rewrite how we see the cosmos. Today, we're pulling back the curtain on 25 astonishing, overlooked facts about the universe's origin, secrets lost in textbooks, buried in ancient stardust, or whispered only in the language of distant galaxies. Think about the last time you looked up at the night sky and felt that tug of wonder. That's the feeling we're chasing, not just the polished, familiar stories of the Big Bang, but the strange, the unexpected, the moments that make scientists pause and say, "Wait, that shouldn't be possible." Like cosmic breadcrumbs, these clues lead us deeper into questions we didn't even know to ask. Did you know, for example, that the universe might have had a false start before the Big Bang? Or that the very fabric of reality could be stitched together with echoes of universes that existed before ours? These aren't science fiction, they're real theories, real enigmas waiting to be unraveled. This isn't just a list, it's a journey back to the very edge of time. We'll explore how ancient light holds secrets billions of years old, why the universe might be shaped like a hall of mirrors, and what ghostly remnants of the cosmic dawn are still hiding in plain sight. By the end, you won't just see the cosmos differently, you'll feel it. The universe's origin story is wilder, more mysterious, and more alive than we've been taught. So let's begin where all great stories do, at the beginning. Or is it really the beginning? Strap in, we're about to rewrite the past. The moment we think we've pinned down the age of the universe, another wrinkle emerges in the cosmic tapestry. Take the Big Bang, our most widely accepted origin story, with its neatly calculated age of 13.8 billion years. But what if that number is off by billions? Recent studies analyzing the cosmic microwave background, the faint glow left over from the universe's infancy, have uncovered strange inconsistencies. Some regions appear cooler than they should be, while others show unexpected fluctuations in density. These aren't just minor quirks, they could be cracks in the foundation of our cosmic timeline. One theory gaining traction is the tired light hypothesis, a radical rethink of how light behaves over unimaginable distances. Instead of space stretching due to expansion, this idea suggests light loses energy as it travels, making distant galaxies seem farther away, and the universe appear older than it truly is. Imagine light as a marathon runner gradually slowing down, its steps measured differently than we assumed. If true, the Big Bang might not have been the explosive beginning we envision, but part of a much longer, slower unraveling of reality. Then there's the startling possibility of a pre-Big Bang era. Some models propose that our universe is merely one chapter in an endless cycle of contraction and expansion, like a cosmic heartbeat. If remnants of a previous universe linger in the background radiation, it could mean the cosmos is far more ancient than our telescopes can yet see. Think of it like finding fossils embedded in the walls of a cave, hinting at an era before the cave even existed. These anomalies force us to confront a humbling truth: our cosmic clock might be missing gears. Every time we think we've measured the universe's birth certificate, new data scribbles in the margins, whispering that the story is far from complete. Somewhere in the first few minutes after the Big Bang, when the universe was just a seething soup of particles, nature was supposed to follow a very specific recipe. Scientists call it Big Bang nucleosynthesis, the moment when protons and neutrons fused into the first atomic nuclei. According to the math, this process should have left behind precise amounts of hydrogen, helium, and just a pinch of lithium, scattered like cosmic seasoning through the newborn cosmos. But here's where things get strange. When astronomers peer back at ancient stars, living fossils from the universe's youth, they find something baffling: the lithium is missing. Not just a little less than expected, but a staggering 2/3 short of what the equations demand. This isn't a small accounting error. It's a gaping hole in our understanding of how matter itself was forged. Lithium might seem insignificant compared to hydrogen's abundance, but its absence is like finding a crime scene where a key piece of evidence has vanished. The rules of nuclear physics, tested and trusted in laboratories for decades, insist those lithium atoms should be there. So where did they go? Some theories suggest exotic physics at play, perhaps undiscovered particles subtly altering nuclear reactions in the early universe's extreme environment. Others propose that lithium was later destroyed inside ancient stars, though that raises new questions about how it vanished so thoroughly without a trace. Then there's the radical possibility that our models of nucleosynthesis are incomplete. Imagine baking a cake where the recipe says sugar should be in the batter, but you open the oven to find none. You'd question the recipe, the ingredients, even the oven itself. That's the scale of this mystery. If the laws governing the universe's first nuclear reactions weren't quite what we think, it could mean rewriting chapters in physics textbooks. This lithium deficit isn't just a curiosity, it's a cosmic whisper that something fundamental is eluding us. Whether it's hidden physics, overlooked stellar processes, or a flaw in our very understanding of the Big Bang's aftermath, one thing is clear. The universe's opening act still holds secrets that defy even our most confident predictions. And that missing lithium, it's more than an anomaly. It's a clue waiting to crack open a deeper truth about how everything began. Dark matter is the universe's most frustrating magic trick. It shapes everything we see, yet refuses to reveal itself. When the first stars flickered to life in the cosmic dawn, they didn't just ignite in empty space. They were coaxed into existence by vast, invisible scaffolding, dark matter's gravitational pull. Picture a sculptor shaping clay in the dark. You can't see their hands, but you watch the form emerge. That's how dark matter worked in those early epochs, gathering ordinary gas into dense pockets where gravity finally sparked the first stellar fires. But here's the twist. The way those first stars formed doesn't quite match our simulations. They shouldn't have been so bright, so massive, or so fast. Something's missing in the recipe. Theories abound. Maybe dark matter wasn't just a passive scaffold, but an active participant. Its particles interacting in ways we haven't accounted for. Some models suggest warm, dark matter, moving faster than expected, could have smoothed out small clumps, delaying star formation in certain regions while accelerating it elsewhere. Others propose dark matter might have even collided with itself, creating friction that altered how structures grew. Imagine trying to bake bread while someone keeps adjusting the oven temperature. You'd get uneven results, just like those puzzling early galaxies. Then there's the eerie evidence from 21-centimeter radiation, the faint radio whispers of hydrogen from the universe's toddler phase. The signal is cooler than predicted, as if something, perhaps dark matter, was siphoning heat from the gas. Could dark particles have absorbed energy like cosmic sponges? It's a haunting possibility, one that would mean dark matter didn't just hold the universe together but changed its very temperature. Every clue deepens the mystery. We're left staring at cosmic fingerprints, knowing the hand that made them is nothing like our own. If dark matter played by different rules in the cosmic dawn, it might still be playing by them today, hidden in plain sight, rewriting the universe's first chapter from the shadows. The cosmic web is supposed to be a sprawling network, filaments of galaxies strung across the universe like threads in a grand tapestry. But scattered throughout this structure are eerie, gaping voids so vast they could swallow thousands of Milky Ways without a trace. These aren't just empty spaces, they're cosmic deserts, regions where galaxies should exist but don't. The Boötes Void, one of the largest ever discovered, stretches over 300 million light-years, yet contains barely 60 galaxies. To put that in perspective, our local corner of space would pack thousands into the same volume. Why does this matter? Because according to our best models of cosmic evolution, voids this large shouldn't exist. The universe's structure is shaped by gravity pulling matter into dense clusters and leaving sparse gaps, but the scale of these voids pushes the limits of what's statistically possible. It's as if someone erased entire sections of the canvas. Some theorists suggest exotic explanations. Perhaps dark energy, the mysterious force accelerating the universe's expansion, acts unevenly, stretching these regions faster than the surrounding cosmos. Others speculate about primordial quantum fluctuations frozen into the fabric of reality during the Big Bang, leaving behind bubbles of nothingness like cosmic scars. Then there's the unsettling observation that some voids seem too empty. Even the sparse galaxies within them often cluster along the edges, as if repelled by an unseen force. Could there be unknown physics at work, a fifth fundamental force, or something stranger? One fringe idea posits these voids as evidence of collisions with other universes in the multiverse, their boundaries etched into our own. These gaps in the cosmic web aren't just curiosities, they're challenges to our understanding of how the universe organizes itself. Every time we map a new void, it whispers the same unsettling question: what if we've only been reading half the story? Quasars should be chaotic cosmic lighthouses flickering independently, their spin axes pointing randomly across the sky. Yet when astronomers mapped over 100 of these ultra-bright galactic cores, a pattern emerged that defied all expectations. Their rotational axes weren't just aligned in small clusters, they were synchronized across scales spanning billions of light years, distances so vast no known force should be able to coordinate them. It's as if scattered whirlpools in an ocean were all spinning in the same direction, despite being separated by entire continents. This alignment isn't just odd, it's a direct challenge to the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions at large scales. If quasars are telegraphing some unseen order, it could mean the cosmos has a hidden skeleton, a colossal structure woven into space-time itself, tugging on these cosmic beacons like invisible strings. One controversial explanation points to cosmic strings, hypothetical defects in space-time left over from the universe's birth, acting as celestial puppet masters. Or perhaps the early universe's magnetic fields, imprinted during inflation, stretched to proportions we're only now glimpsing through these aligned quasars. Even stranger, some theories suggest this alignment might be a relic of pre-Big Bang physics, a fingerprint of processes that operated when reality was mere quantum froth. Picture a frozen lake where cracks form in perfect geometric patterns, betraying forces that shaped it while it was still liquid. If quasars are cosmic cracks, their alignment hints at a symmetry baked into existence before time began. Yet skepticism lingers. Could this be a fluke, a statistical illusion? The odds are slim, like shuffling a deck of cards and dealing 52 aces in a row. With every new quasar mapped, the signal grows harder to dismiss. Whatever's orchestrating this galactic ballet, one thing's clear: the universe's scaffolding might be far stranger, far more intricate than we ever dared imagine. We think of space as the coldest place imaginable, a vast, dark freezer where temperatures plunge near absolute zero. But when astronomers took the universe's temperature, they got a shock. The cosmos isn't as frigid as it should be. In fact, scattered throughout the voids between galaxies, there's a faint, persistent warmth, as if some unseen furnace has been left running since the dawn of time. This excess heat defies conventional physics. After all, space is mostly empty, with particles spread so thinly that temperatures should hover just above the coldest possible mark. Yet measurements of the cosmic microwave background, the afterglow of the Big Bang, reveal patches that are inexplicably warmer, like finding hidden radiators buried in the walls of an ice cave. Even more puzzling, this heat isn't evenly distributed. It clusters in ways that can't be explained by known energy sources, stars, black holes, or even the residual warmth of the universe's fiery birth. One daring explanation points to dark matter's hidden chemistry. If dark particles aren't completely stable, if they decay over eons into lighter, energetic particles, they could be leaking heat into the cosmos like slow-burning embers. Imagine a lump of coal glowing unseen beneath a blanket, warming everything around it without leaving visible light. That could mean dark matter isn't just an invisible anchor for galaxies, but an active participant in the universe's thermal history, shaping temperatures in ways we're only beginning to detect. There's also the eerie possibility of primordial energy left over from the universe's first seconds. Some theories suggest quantum fields flickering during inflation may have imprinted pockets of excess heat into the fabric of space itself. Think of it like kneading dough with uneven warmth. Some regions baked faster than others, leaving lasting hotspots frozen into the cosmic structure. Or perhaps this warmth is evidence of something even stranger: collisions between parallel universes in the multiverse, their boundaries leaking energy into ours like steam through a cracked window. It sounds like science fiction, but the numbers don't lie. The universe isn't just losing heat as it expands, it's holding onto traces of warmth that shouldn't exist. Every anomalous degree is a clue, a whisper from the cosmos that our thermal maps are missing entire chapters of the story. This isn't just a scientific discrepancy. It's a call to rethink what we know about energy, matter, and the hidden machinery of reality. Because if the universe is hotter than it's supposed to be, something or someone left the heat on. And we're just beginning to trace the hand that turned the knob. Phantom energy sounds like something from a cosmic horror story, and in a way it is. Imagine a force so destructive that it could shred the very fabric of space-time, unraveling galaxies, stars, and even atoms in a catastrophic crescendo known as the Big Rip. This isn't just another flavor of dark energy, it's a hypothetical nightmare scenario lurking in the equations of cosmology. While dark energy gently pushes the universe apart, accelerating its expansion, phantom energy would do so with a vengeance, growing stronger over time until reality itself is torn apart at the seams. The math behind this phenomenon is deceptively simple. Dark energy's behavior is tied to a number called the equation of state parameter, represented by W. For ordinary dark energy, W hovers around -1. But if that value dips even slightly lower, if W crosses into phantom territory, the consequences become apocalyptic. The universe wouldn't just expand, it would accelerate exponentially, overwhelming gravity's pull, then electromagnetism, and eventually the nuclear forces holding matter together. Picture a rubber band stretched so taut it snaps, except here the rubber band is existence itself. Yet proving phantom energy exists is like chasing a shadow. Current telescopes can't directly measure W with enough precision to confirm or rule out this terrifying possibility. The best clues come from supernova, baryon acoustic oscillations, and other cosmic yardsticks, but the data remains frustratingly ambiguous. Some observations even flirt with W values perilously close to the phantom zone, leaving scientists uneasy. Could the universe already be on a slow-motion path to self-destruction? Then there's the bizarre twist. Phantom energy might leave behind eerie witnesses to its presence. Theoretical models suggest that if phantom energy dominates, the universe could eventually spawn infinitely energetic particles called Big Rip singularities, points where space-time curvature becomes infinite. These wouldn't be black holes, they'd be something far stranger, like cosmic stitches straining to hold together a reality coming undone. Skeptics argue phantom energy is just a mathematical quirk, a ghost in the machinery of cosmology. After all, no known quantum field naturally produces such extreme behavior. But that's the unsettling beauty of this idea. It forces us to confront how little we truly understand about the universe's fate. Whether phantom energy is real or not, its mere possibility underscores a humbling truth. The cosmos might have expiration mechanisms we haven't even begun to fathom. So while we're not packing our existential survival kits just yet, the phantom energy hypothesis remains a haunting reminder. The universe doesn't owe us a gentle end. And somewhere in the equations scribbled on whiteboards and buried in supercomputer simulations, there might be a clue that our reality's finale will be far stranger than we dared imagine. The Hubble constant is supposed to be one of the most straightforward numbers in cosmology, a single value representing how fast the universe is expanding. But here's the problem: depending on how you measure it, you get two starkly different answers, and the gap between them isn't just a rounding error. It's a full-blown crisis shaking the foundations of modern astrophysics. One method uses the cosmic microwave background, the afterglow of the Big Bang, as a cosmic yardstick. By analyzing tiny temperature fluctuations in this ancient light, scientists can extrapolate how quickly space has stretched over time. This approach gives a Hubble constant of around 67 kilometers per second per megaparsec, meaning for every million parsecs of distance, space expands 67 kilometers faster each second. But then there's the second method, which relies on nearby celestial lighthouses, Cepheid variable stars and Type Ia supernova. These objects have predictable brightness, allowing astronomers to gauge distances and track expansion directly. The catch: this method spits out a Hubble constant closer to 73, a significant jump from the CMB-derived value. At first glance, a difference of 6 might not sound earth-shattering, but in the precise world of cosmology, it's like two clocks ticking at irreconcilable speeds. So who's wrong? The unsettling answer might be neither. If both methods are correct and repeated observations suggest they are, then our understanding of cosmic history is missing something fundamental. Perhaps dark energy isn't constant but evolves over time, or maybe unknown particles from the early universe are subtly altering expansion rates. Some theorists even speculate about a dark sector of physics where undiscovered forces influence the cosmos in ways we haven't yet modeled. The implications are staggering. If the Hubble tension holds, it could mean rewriting textbooks on how the universe ages, how structures form, and even how it will end. Because when the numbers refuse to agree, it's not just a puzzle, it's a sign that the cosmos is keeping secrets. Imagine a universe that never stops giving birth, not just once but endlessly, spawning bubble realities like foam in an infinite cosmic sea. This was the breathtaking promise of eternal inflation, a theory that once seemed poised to rewrite our understanding of existence. Unlike the standard Big Bang narrative, eternal inflation proposed that the explosive expansion of space-time didn't just happen once in our universe, it's happening perpetually, with new universes budding off in a fractal cascade of creation. Picture a pot of water boiling eternally, with each bubble rising to the surface representing an entirely new cosmos, each with its own laws of physics, its own version of time. At its peak, this idea was revolutionary. It elegantly explained why our universe appears so finely tuned for life. If infinite bubbles exist, some would inevitably land on the right combination of constant gravity just strong enough, electromagnetism just weak enough, to allow galaxies, stars, and eventually us to emerge. The multiverse became a cosmic lottery, with life as the rare winning ticket. But here's the twist: the same feature that made eternal inflation so compelling, its endless creativity, also became its greatest weakness. Critics began to ask, if the theory predicts everything by allowing all possible universes, does it actually explain anything? Science thrives on falsifiability, the ability to test and potentially disprove ideas. But how do you test a multiverse you can never observe, where every imaginable outcome plays out somewhere? The theory became a victim of its own ambition, drifting into the realm of philosophy rather than physics. Then came the observational blows. Eternal inflation predicted distinct patterns in the cosmic microwave background, subtle fingerprints of neighboring universes bumping against ours. But when scientists scoured the data, those telltale signs were conspicuously absent. Even the most precise measurements of the CMB revealed no evidence of cosmic collisions, no bruises from other bubbles. The silence was deafening, yet the idea hasn't vanished entirely. Some researchers, unwilling to abandon its elegant framework, have proposed modified versions, slow roll, inflation, or mechanisms that make bubble collisions rarer. Others suggest we're looking for the wrong evidence, that the multiverse's signatures might be hidden in gravitational waves or quantum entanglement. But until a smoking gun emerges, eternal inflation remains in limbo, too beautiful to discard, too elusive to prove. What's fascinating isn't just the theory's rise and fall, but what its struggle reveals about science itself. Even the most brilliant ideas must face the unforgiving light of evidence. Eternal inflation's legacy is a cautionary tale, a reminder that the universe owes us neither simplicity nor answers. And perhaps that's the most profound truth of all, that the search for origins is as much about learning how to ask questions as it is about finding the answers. At the universe's birth, matter and antimatter should have been created in perfect balance particles, and their mirror opposites emerging in equal measure, destined to annihilate each other in bursts of pure energy. Yet here we are, in a cosmos filled with galaxies, planets, and life, all built from matter, the antimatter almost entirely gone. This baffling imbalance, known as baryon asymmetry, is one of physics' most glaring unsolved mysteries. If the Big Bang played fair, everything should have cancelled out, leaving behind a sea of radiation and nothing else. So why does matter dominate? The first clue came from a subtle glitch in nature's symmetry. In the 1960s, researchers discovered CP violation, a phenomenon where particles called kaons decay slightly differently from their antimatter counterparts. It was like finding a coin that lands on heads just a fraction more often than tails. This tiny asymmetry, later observed in other particles like B mesons, hinted that the universe might have a hidden preference for matter. But here's the catch: the observed CP violation is far too weak to explain the overwhelming matter surplus we see today. It's as if someone left a faucet dripping in a desert and claimed it filled an ocean. Desperate for answers, physicists turn to more exotic possibilities. One leading theory involves neutrinos, those ghostly particles that barely interact with matter. If neutrinos are their own antiparticles, a property called Majorana fermions, they could have triggered a process called leptogenesis in the early universe. Picture a cosmic domino effect, neutrinos decaying unevenly, producing more electrons than positrons, which then tip the scales for quarks, cascading into the matter-dominated reality we know. Then there's the specter of primordial black holes. Some models suggest these ancient gravitational traps, formed in the universe's first seconds, could have selectively swallowed antimatter, effectively erasing it from the cosmic ledger. Imagine a sieve that only catches red marbles, leaving blue ones behind, except here, the marbles are particles and the sieve is a black hole with inexplicable taste. But the boldest ideas lurk beyond known physics. Grand unified theories predict heavy, unstable particles called X-bosons that decay unevenly into matter and antimatter. If these existed fleetingly after the Big Bang, their asymmetric demise could have seeded our material universe. Even wilder is the notion that antimatter domains still exist, vast regions of space where antistars and antiplanets formed, separated from us by unimaginable distances. The stakes couldn't be higher. Solving baryon asymmetry isn't just about balancing an equation. It's about understanding why anything exists at all. Every atom in your body, every star in the sky is here because nature broke its own rules, and we still don't know how. Until we do, the universe's greatest magic trick remains unexplained, pulling existence itself out of an empty hat. The universe is unimaginably vast, trillions of galaxies, each with billions of stars, countless planets orbiting in the darkness. With odds like that, the cosmos should be teeming with life, buzzing with the radio chatter of alien civilizations. Yet when we listen, all we hear is silence. This eerie absence is the heart of the Fermi paradox. If life should be common, where is everyone? The answer might lie not in our present, but in the universe's violent infancy. Think back to those first chaotic moments after the Big Bang. The conditions for life-stable planets, the right mix of elements, gentle enough radiation, weren't just rare, they were nearly impossible. For hundreds of millions of years, the universe was a hellscape of searing plasma, where even atoms couldn't hold together. Life needed not just time, but a cosmic Goldilocks zone. Stars old enough to forge heavy elements like carbon and oxygen, yet young enough to avoid bathing their planets in deadly radiation. Could it be that our universe simply hasn't been habitable long enough for civilizations to arise elsewhere? But there's a darker twist. Some theories suggest that advanced civilizations might inevitably face extinction-level filters, catastrophes baked into the fabric of physics itself. Imagine a galaxy where intelligent life emerges only to discover that harnessing energy at scale triggers vacuum decay, a runaway quantum effect that erases reality like a flame-consuming paper. Or perhaps technological progress always leads to AI-driven self-destruction, a grim pattern repeating across the cosmos. These aren't sci-fi tropes, they're legitimate risks physicists take seriously. Then there's the haunting possibility that we truly are alone. The Great Filter theory posits that some step in the chain from primordial soup to spacefaring intelligence is so improbable that Earth might be a fluke. Maybe the jump from single-celled to multicellular life is a near-impossible barrier, or perhaps the stability required for complex evolution is a cosmic lottery few planets win. Yet silence isn't always emptiness. Some researchers argue that advanced civilizations might communicate in ways we can't yet detect using neutrino beams, quantum entanglement, or structures built around stars. Or maybe they've transcended physical forms entirely, existing as digital consciousnesses in Dyson swarms, invisible to our primitive telescopes. The Fermi paradox forces us to confront a humbling truth. The universe's origins might have set the stage for a tragedy where life flickers into existence, only to vanish before neighbors can meet. Whether the answer lies in physics, biology, or something beyond our understanding, one thing is clear. The silence isn't just a mystery, it's a mirror reflecting back our own fragility in the cosmic dark. The universe glows in ways we're only beginning to understand, not just in the light we see, but in hidden infrared whispers that defy explanation. When astronomers first mapped the cosmic infrared background, they expected a predictable tapestry of heat from known galaxies and dust. Instead, they stumbled upon patches of eerie, unexplained light excess radiation with no obvious source, as if someone had scattered bonfires across the cosmos and left them burning in secret. These anomalies aren't just statistical noise, they're cosmic breadcrumbs pointing to phenomena so exotic they could rewrite our understanding of the early universe. One tantalizing possibility: this glow might be the dying embers of the very first stars, monstrous, short-lived giants called population 3 stars. Unlike modern stars, these primordial behemoths formed from pure hydrogen and helium, untouched by heavier elements. Theorized to be hundreds of times more massive than the Sun, they would have blazed furiously before collapsing into black holes or exploding in hypernova, their light stretched by cosmic expansion into the infrared we detect today. Finding their afterglow would be like uncovering fossilized footprints from the universe's first steps. But there's a catch. Population 3 stars should have left other traces, like specific chemical signatures in ancient gas clouds. So far, those fingerprints are missing, leaving the infrared excess without a clear parent. This gap has led to a wilder hypothesis. What if the glow isn't from stars at all, but from dark matter itself? Certain theories suggest dark matter particles could decay or collide, releasing energy as they annihilate one another. If true, these invisible particles might be painting the cosmos with infrared light, turning the universe's darkest ingredient into an unexpected artist. Then there's the middle ground, rogue planets ejected from their star systems and drifting cold and alone, warmed slightly by internal heat. Or perhaps vast clouds of nanodiamonds reflecting starlight in ways we haven't yet modeled. Each explanation teases at a different cosmic story, from the violent deaths of first-generation stars to the subtle unraveling of dark matter's secrets. What makes these infrared anomalies so thrilling is their refusal to fit neatly into existing frameworks. They're not just puzzles to solve, they're invitations to rethink the boundaries of astrophysics. Every unexplained photon carries a message, one that might lead us to discoveries far stranger than we've dared to imagine. The Big Bang looms large in our cosmic origin story, the moment when time, space, and matter erupted into existence. But what if that fiery beginning wasn't the true starting line? Some of today's boldest physics theories suggest the universe might have a shadowy prehistory, a phase before the bang where the rules of reality were utterly alien. Take loop quantum gravity, a framework that reimagines spacetime not as smooth and continuous, but as a weave of tiny, indivisible threads. In this view, the Big Bang wasn't a creation ex nihilo, it was a rebound, a cosmic bounce from a previous universe that had collapsed inward. Picture a rubber ball hitting the ground with infinite force, only to spring back outward, carrying traces of its past shape into a new existence. String gas cosmology paints an even stranger picture. Here, the early universe was a seething ocean of vibrating strings, the fundamental entities of string theory colliding and entangling in a chaotic dance. Before the bang, these strings might have existed in a hot, dense equilibrium, their interactions eventually triggering the explosive expansion we call inflation. Think of it like a pot of water finally boiling over after endless churning. The Big Bang wasn't the first event, just the most dramatic one in an older, deeper timeline. Then there's the haunting idea of conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose. He suggests that the universe cycles through endless epochs, each ending in a heat death so complete that all particles lose their sense of time and scale. In this eerie twilight, the universe resets and a new Big Bang emerges from the ashes of the old. It's as if the cosmos is a phoenix, dying only to be reborn from its own remains, with faint imprints of past universes lingering in the cosmic microwave background like ghostly fingerprints. What's astonishing about these theories isn't just their creativity, it's their potential to explain lingering mysteries. For instance, if our universe is a rebound, the specific smoothness of the cosmic microwave background might reflect quantum geometry from the pre-bang era. Or if string gas cosmology is correct, the three-dimensional nature of space could emerge from strings preferring certain vibrational states over others. Even Penrose's cycles find tentative support in anomalous Hawking points, warm spots in the CMB that could be radiation from ancient black holes in a prior universe. Yet for all their promise, these ideas lie on the edge of testability. How do you probe a reality that existed before time itself? Some clues might lie in gravitational waves, the ripples in spacetime that could carry echoes of pre-bang physics. Others could emerge from subtle patterns in the quantum noise of the early universe, detectable only by next-generation telescopes. The most profound implication isn't just a rewrite of cosmic history, it's the realization that beginning might be a human concept, not a physical one. If these theories hold, the Big Bang wasn't a true origin, just a pivot point in an endless cycle of transformation. The universe, it seems, has always known how to reinvent itself. And if we're lucky, the next decade of observations might finally let us read the shadows it left behind. Magnetic fields are the universe's silent architects, invisible threads woven through space, guiding the birth of galaxies with an unseen hand. While most cosmic origin stories focus on gravity and dark matter, primordial magnetism might have played a far greater role than we've given it credit for. Picture the early universe not as a smooth, featureless soup, but as a turbulent sea crisscrossed with magnetic currents, their influence subtly shaping where matter would eventually clump together. These fields, weaker than a refrigerator magnet but stretching across light years, could have been the hidden scaffolding for everything we see today. The evidence lies in the cosmic web itself. Galaxies don't just cluster randomly, they align along vast filaments like beads on a string. Traditional models attribute this structure solely to gravity's pull, but simulations that include primordial magnetic fields tell a different story. When researchers added even faint magnetism to their calculations, something remarkable happened. Galaxies formed earlier and more efficiently. Their swirling gas funneled along magnetic lines like water following grooves in a slope. It's as if the universe had invisible rivers directing the flow of matter long before stars ignited. But where did these ancient fields come from? One theory points to the universe's infancy, when the seething plasma of the Big Bang's aftermath churned like a stormy ocean. Tiny electric currents generated by particles moving at near light speeds could have amplified weak magnetic seeds into sprawling cosmic webs. Imagine blowing on a dandelion, the faintest breath scattering seeds in a pattern that grows into a field of flowers. Similarly, those initial ripples might have blossomed into the magnetic structures we infer today. Even stranger, some models suggest these fields could explain dark matter's elusive behavior. If dark particles carry an electromagnetic charge, a controversial but tantalizing idea, their interaction with primordial magnetism might explain why they clump in ways that defy gravity alone. Think of iron filings organizing around a magnet, invisible forces creating order where none should exist, yet mysteries remain. Why do some galaxy clusters show coherent magnetic alignment over distances too vast for known physics? And how do these fields persist for billions of years without dissipating? The answers might lie in cosmic feedback loops, where collapsing gas reignites magnetism in a self-sustaining cycle, or in exotic physics at play during the universe's first seconds. What's clear is this: magnetism isn't just a footnote in cosmic history. It could be the missing ingredient that explains why the universe looks the way it does, a whisper from the dawn of time, still echoing in the structure of everything around us. And if we learn to read its hidden language, we might finally understand how the cosmos built itself from scratch. Black holes shouldn't have had time to grow so big so fast. Yet when astronomers peer back to the universe's infancy, they find supermassive black holes already lurking in the cosmic dawn, monsters weighing billions of times the mass of our sun, existing when the cosmos was less than 1 billion years old. This isn't just surprising, it defies everything we know about how black holes form. Normally, they start small, feeding on gas and stars over eons to reach colossal sizes. But these ancient behemoths didn't have eons. They had what amounts to a cosmic blink of an eye. So how did they get there? The answer might rewrite our understanding of the universe's first moments. One leading theory suggests these black holes were born not from dying stars, but from the direct collapse of enormous gas clouds in the early universe. Picture a nebula so massive and dense that it skips the star-forming stage entirely, imploding straight into a black hole like a house collapsing into its own foundation. These direct collapse black holes could have formed with masses thousands of times greater than a typical stellar black hole, giving them a head start in the feeding frenzy of the young cosmos. Simulations show that in the right conditions, intense ultraviolet radiation preventing gas from fragmenting into stars, these primordial giants could have emerged as cosmic titans before the first galaxies even finished assembling. But there's an even wilder possibility: primordial black holes forged not from gas or dying stars, but from the violent turbulence of the Big Bang itself. In the universe's first second, when space was a seething quantum froth, microscopic fluctuations in density might have created pockets so dense they pinched off into black holes, some as small as atoms, others as massive as planets or stars. Over time, these primordial seeds could have grown by swallowing surrounding matter, merging with one another, or even feeding on the fabric of space-time itself. If they exist, they'd be relics of a time before atoms, before light, before the laws of physics as we know them settled into place. The trouble is, we've never definitively found a primordial black hole. They'd be nearly invisible, their tiny sizes making them elusive to telescopes, yet indirect clues tantalize. Some models suggest these ancient objects could explain dark matter, their gravitational influence shaping galaxies without emitting light. Others point to strange gravitational lensing events, brief flashes in the sky where something invisible but massive bends starlight, as if a rogue black hole drifted between us and the stars. Then there's the middle ground. Perhaps supermassive black holes grew through a combination of both paths. Early gas collapses could have jump-started their growth, while mergers with primordial black holes supercharged them further. It's like a cosmic buffet where the hungriest guests had multiple ways to pile their plates. What's striking isn't just the mystery, but what it reveals about the universe's flexibility. The laws of physics allow for multiple roads to the same impossible destination. Whether through collapsing gas, quantum birth pangs, or some process we haven't yet imagined, the universe found a way to build giants in the dark. And until we spot the smoking gun, a primordial black hole caught in the act, or a distant quasar, are too young to exist, these cosmic titans will keep challenging our assumptions about how reality works at its most extreme scales. Amid the subtle ripples of the cosmic microwave background, the afterglow of the Big Bang, there's a patch of sky that doesn't belong. The so-called cold spot, a region hundreds of times larger than a full moon, blazes with a temperature drop so extreme it defies easy explanation. At first glance, it might seem like a statistical fluke, a random quirk in the data. But the odds of such a cold anomaly appearing by chance are less than 1 in 100,000, raising the unnerving possibility that we're staring at a cosmic wound, a scar from the universe's birth that never fully healed. One leading theory points to a supervoid, an unimaginably vast bubble of space nearly devoid of galaxies and matter, stretching across billions of light years. If such a void exists along our line of sight, photons from the CMB passing through it would lose energy as they climb out of its gravitational well, a phenomenon called the integrated Sachs-Wolf effect. Think of a hiker trudging up a mountain, arriving exhausted on the other side. The cold spot would be the cosmic equivalent of that fatigue, a telltale sign of light struggling across an empty frontier. But here's the problem. Surveys haven't found a void large or deep enough to account for the temperature drop. Either we're missing something in the surveys, or the void's properties defy conventional physics. Then there's the far more exotic possibility, a cosmic texture. In the early universe, phase transitions shifts in the fundamental state of matter, and energy might have created defects in spacetime itself, like cracks forming in ice as it freezes. A texture would be one such defect, a knot of concentrated energy that left behind a gravitational imprint as it unraveled. If the cold spot marks where one of these textures once existed, it would be evidence of physics operating at energies trillions of times higher than anything achievable in particle colliders, a frozen whisper from the universe's first trillionth of a second. Skeptics argue the cold spot could still be an illusion, a chance alignment of smaller voids, or even an artifact of how we've processed the CMB data. But the texture hypothesis lingers because it offers something rare, a testable prediction. If the cold spot's polarization patterns, the subtle swirls in the light's orientation match what textures would produce, it could be the smoking gun for physics beyond the standard model. What makes this mystery so compelling isn't just the anomaly itself, but what it represents. The cold spot might be a flaw in our maps, or it could be a window into a hidden layer of reality, a place where the universe's infancy left behind clues written in the language of gravity and quantum fields. Either way, it's a reminder that even our best cosmic snapshots might still be missing pages from the story. The idea of an endless cosmic cycle of universes expanding, collapsing, and reborn feels almost poetic in its symmetry. Long before the Big Bang became cosmology's cornerstone, thinkers like Hindu sages and Greek philosophers envisioned time as a wheel, turning through ages of creation and destruction. But in the 20th century, this ancient intuition found scientific footing in the oscillating universe model, a daring alternative to the one and done Big Bang. Picture a cosmic lung inhaling matter inward in a big crunch before exhaling outward in a new bang, over and over for eternity. At first glance, it's an elegant solution to the question of origins. No need for a mysterious beginning when the universe simply reinvents itself. Yet the cyclic model hit a wall with the discovery of dark energy. In the 1990s, astronomers realized the universe's expansion wasn't slowing down as expected. It was accelerating, propelled by an unknown force pushing galaxies apart. This shattered the dream of an eventual collapse, leaving the oscillating universe without its crucial second act. But like all great ideas, it refused to die. Revised versions of the cyclic theory emerged, weaving in quantum mechanics and higher dimensional physics to explain how a universe could bounce even with dark energy at play. One proposal involves colliding branes, hypothetical membranes floating in a higher dimensional space, whose periodic crashes could trigger new bangs without requiring a full contraction. Imagine two sheets of paper fluttering in a breeze, occasionally smacking together with enough force to spark a new reality inside them. What keeps these theories alive isn't just their audacity, but their ability to explain cosmic quirks the standard model struggles with. For instance, the unnerving smoothness of the early universe's temperature, a puzzle traditionally solved by inflation, might instead reflect conditions inherited from a prior cycle. Like kneading dough, each collapse and rebirth could homogenize the cosmos, erasing wrinkles left by the previous incarnation. Even the arrow of time, which mysteriously points from order to disorder in our universe, might flip during a bounce, resetting entropy like a cosmic egg timer. Not everyone's convinced. Critics point to the lack of observable evidence, no telltale scars from a prior universe, no echoes of a crunch in the gravitational wave background. And without a precise quantum theory of gravity, the mechanics of a bounce remain speculative math, not testable science. But the cyclic universe's enduring appeal lies in its defiance of finality. In a cosmos that feels increasingly ephemeral, doomed to expand into cold, empty darkness, the idea of endless renewal offers a strange kind of comfort. After all, if the universe has done this before, who's to say it won't find a way to begin again? Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace, as if they weren't even there. These nearly massless particles, born in the hearts of stars and the fury of the Big Bang, barely interact with ordinary matter. Yet despite their elusive nature, they might have played a crucial role in sculpting the cosmos on the grandest scales. The key lies in their mysterious mass. For decades, physicists assumed neutrinos were weightless, zipping through space at the speed of light. Then came the shocking revelation: they do have mass, just unimaginably tiny, so small we still don't know exactly how much. That uncertainty isn't just a minor technicality, it's a gap in our understanding of how the universe built its largest structures. Imagine the early cosmos as a crowded dance floor where matter is trying to clump together under gravity's pull. Neutrinos moving at near light speeds would have acted like subatomic bumper cars, smashing into these nascent clusters and scattering them apart. The lighter they were, the faster they'd zip around, smoothing out density variations like a cosmic rolling pin. But if they're slightly heavier than current estimates suggest, their sluggishness would have left more pronounced wrinkles in the cosmic web wrinkles that grew into the galaxies and voids we see today. It's like trying to trace a fingerprint left in wet clay versus hardened stone. The weight of neutrinos determines how deeply they pressed into the universe's blueprint. The evidence for their influence is written in the distribution of galaxies. Surveys reveal that the universe's large-scale structure is slightly more clumped than simulations predict unless you factor in neutrinos with a specific mass range. Add these particles into the equations and suddenly the models align with reality. But here's the catch, we still can't pin down their exact mass. Experiments like Katrin, which tries to weigh neutrinos by tracking the energy of their decay products, have only set up a limit. Other projects, such as upcoming observations by the Vera Rubin Observatory, aim to measure their impact on cosmic structure with unprecedented precision. What makes neutrinos truly fascinating isn't just their role in shaping galaxies, it's the possibility that they might be hiding secrets beyond the standard model. Some theories suggest they could be their own antiparticles, a property that might explain why the universe has more matter than antimatter. Others propose sterile neutrinos, an even more elusive variant that could account for dark matter's shadowy presence. Every unanswered question about these ghostly particles is a thread in a larger tapestry. The universe didn't just assemble itself through gravity and dark matter alone. It had silent partners whispering influences from the shadows. And until we measure the weight of a neutrino, we're missing a fundamental piece of the cosmic puzzle. One thing's certain, the lighter they are, the heavier their impact on our understanding of everything. The universe runs on numbers constants so precise that altering any one of them by a hair's breadth would unravel reality as we know it. The strength of gravity, the mass of an electron, the energy binding atomic nuclei, each seems meticulously dialed to values that allow stars, planets, and life itself to exist. It's as if someone tuned a cosmic radio to the exact frequency where chemistry, structure, and complexity could emerge from chaos. But this perfection isn't just remarkable, it's deeply unsettling. Why does the universe appear so exquisitely fine-tuned for life? One approach to this riddle is the anthropic principle, the idea that we observe these constants precisely because they're the only ones compatible with our existence. Imagine a puddle marveling at how perfectly its hole fits its shape. The universe isn't tailored for us. We're the accidental beneficiaries of its parameters. On its own, this explanation feels almost like a shrug, a philosophical stopgap, but coupled with the multiverse theory, it transforms into something profound. If countless universes exist each with randomly assigned constants, then statistically, a handful would land in the life-permitting sweet spot. We just happen to live in one of the lucky ones. The multiverse idea isn't monolithic. In some versions, bubble universes nucleate eternally, each with different physical laws. Others propose higher dimensional membranes colliding in a bulk space, spawning realities like droplets from a splash. There's even the quantum multiverse, where every decision point branches history into parallel timelines. What unites them is the audacious claim that our universe's fine-tuning isn't a miracle. It's an inevitability of probability played out across infinite iterations. Critics argue this simply kicks the can down the road. Who or what set the rules governing the multiverse itself? And why do those meta-laws permit life-friendly universes at all? Some physicists, like Lee Smolin, propose a form of cosmic natural selection. Universes that give birth to black holes may spawn new universes with slightly tweaked constants, leading to an evolutionary pressure toward life-friendly physics. Think of it as a Darwinian take on cosmology, where black holes are the universe's way of reproducing. Yet the fine-tuning puzzle has even wilder solutions. What if the constants aren't fixed but dynamic, evolving over time like cosmic climate? Or what if consciousness itself plays a role in shaping them, as some interpretations of quantum mechanics suggest? The unnerving truth is that every explanation circles back to a deeper mystery. Why does anything exist in a form that allows something like us to ponder it? The constants might be the universe's ultimate lock, and we're still fumbling for the key. Whether the answer lies in multiverses, meta-laws, or something beyond our current imagination, one thing's clear: the cosmos isn't just stranger than we suppose. It's stranger than we can suppose, and that's the most exhilarating part. Einstein's famous equation tied the cosmos together with a constant, the speed of light, an unchanging limit woven into the fabric of reality. But what if that wasn't always true? In the late 1990s, a handful of physicists dared to suggest a heresy. That light might have raced faster in the universe's infancy, a fleeting anomaly erased by time. This wasn't just a tweak to the rules, it was a rewrite, one that could unravel some of cosmology's tightest knots. Take the horizon problem. The cosmic microwave background shows near-perfect uniformity in temperature across regions of space that, according to standard physics, should never have been in contact. Inflation theory solves this by proposing a faster-than-light expansion of space itself, but variable speed of light, or VSL, offers an elegant alternative. If light traveled exponentially faster in those first moments, distant regions could have exchanged heat and information before the speed limit dropped, leaving behind the smoothness we observe today. Think of it like a classroom where everyone starts whispering at the same time, not because they planned it, but because sound initially traveled faster, letting the message spread instantly before the air grew thick and slowed it down. The implications don't stop there. The universe's missing lithium, that nagging discrepancy between predicted and observed amounts, might find an explanation if nuclear reactions in the early cosmos played out under different light speed rules. Even the delicate balance of dark matter's distribution could reflect a time when physics operated on a different clock. Skeptics pounce on the lack of direct evidence. Unlike inflation, which leaves subtle fingerprints in the CMB's polarization, VSL's traces would be buried deeper, perhaps in quantum fluctuations we can't yet measure. And then there's the thorny question of how light speed changed. Some models invoke shifting dimensions or evolving vacuum energy, while others suggest a hidden connection to dark energy's mysterious push. Yet the theory lingers, kept alive by its sheer explanatory power. It's a reminder that even our most sacred constants might be artifacts of a deeper, stranger truth, one where the rules weren't always written in stone, but in something far more malleable. The speed of light might be the universe's ultimate traffic law, but somewhere in the primordial dark, it could have been little more than a suggestion. String theory whispers of a universe far richer than the three dimensions we know. Beyond the familiar length, width, and height, this framework suggests 6 or 7 additional spatial dimensions curled up so tightly they're invisible to us, like the threads of a carpet woven too fine to see from a distance. These hidden dimensions aren't just mathematical flourishes, they might hold the key to understanding the universe's first moments. If they exist, their geometry could have dictated how forces like gravity and electromagnetism separated during the Big Bang, like invisible hands shaping the clay of reality. Picture a garden hose lying across a lawn. From far away, it looks like a simple line, a one-dimensional object, but up close, you see its surface twist around a second dimension, a hidden circle. String theory proposes our entire cosmos might be like that hose, with extra dimensions coiled at scales trillions of times smaller than an atom. During the universe's explosive birth, these dimensions could have vibrated like guitar strings, their resonant frequencies determining the masses of particles and the strengths of fundamental forces. The reason gravity seems so weak compared to other forces, it might be leaking into these unseen dimensions, its power diluted across realms we can't perceive. The wildest idea is that these dimensions weren't always tiny. Some models suggest they once stretched as large as the observable universe before collapsing into their current microscopic state, a process that could have released enough energy to fuel inflation, the universe's rapid expansion after the Big Bang. Imagine blowing up a balloon, then suddenly cinching part of it shut with a rubber band. The released tension would send shockwaves through the remaining space, not unlike how shrunken dimensions might have jump-started cosmic growth. Yet for all its elegance, string theory faces a glaring problem. We've never detected these extra dimensions. They might reveal themselves through subtle effects, like deviations in gravity at microscopic distances or peculiar particle collisions in accelerators. Some physicists hunt for cosmic signatures, anomalies in the cosmic microwave background that could hint at dimensional wrinkles frozen into the early universe's structure. Others speculate that if dimensions are large enough, gravity waves from black hole mergers might carry echoes of their existence, like sound bouncing through hidden chambers. The stakes couldn't be higher. If extra dimensions are real, they wouldn't just rewrite physics, they'd redefine our place in the cosmos. We might be living in a vast, multidimensional labyrinth, unaware of the walls just beyond our perception. Until evidence arrives, string theory remains a breathtaking hypothesis, a reminder that the universe's deepest truths might be hidden in geometries we're only beginning to imagine. Every galaxy, every star, every planet in the cosmos owes its existence to a ghostly whisper from the dawn of time, a whisper so faint it was born from the chaotic dance of particles smaller than atoms. The vast cosmic web we see today, with its glittering clusters and yawning voids, might trace its origins back to quantum fluctuations in the first trillionth of a second after the Big Bang. These microscopic ripples in space-time, random as static on a radio, somehow stretch to cosmic proportions, becoming the gravitational seeds for everything we know. The irony is that we stumbled onto this cosmic blueprint by accident. In the 1960s, astronomers Arno Penzias and Robert Wilson were troubleshooting a persistent hiss in their radio antenna, a noise they initially blamed on pigeon droppings. After scrubbing the equipment clean, the static remained. That stubborn signal turned out to be the cosmic microwave background, the cooled remnant of the Big Bang's fiery glow. But hidden within its subtle temperature variations were the fingerprints of those primordial quantum jitters, frozen in time like waves solidified in glass. Here's the astonishing part: those fluctuations shouldn't have been visible at all. In the early universe's searing heat, matter and energy were so densely packed that gravity should have smoothed everything out, leaving the cosmos featureless. Instead, quantum mechanics, the strange rules governing the subatomic world, allowed tiny irregularities to persist. Think of it like a pot of boiling water where bubbles don't just vanish but leave behind lasting impressions in the metal. These imperfections, magnified by the universe's rapid inflation, became the scaffolding for galaxies. But the story gets stranger. The pattern of these fluctuations isn't perfectly random. Certain statistical quirks, like slightly larger cold spots in the cosmic microwave background, hint that quantum physics might have operated differently under the extreme conditions of the early universe. Some theories suggest these anomalies could be echoes of a pre-inflation era, shadows of a reality even older than the Big Bang. Others propose that unknown particles, interacting fleetingly in that primordial soup, left behind subtle imprints in the cosmic structure. What's mesmerizing isn't just the science, it's the scale of the transformation. Quantum fluctuations smaller than a proton somehow dictated where galaxies would bloom billions of years later. The Milky Way might exist because of a subatomic shudder in a realm we'll never see. It's as if the universe whispered its blueprint into the void, and we're only now learning to listen. Every time we map a new galaxy cluster, we're not just charting space, we're reading a message from the first moment of time itself, written in the language of probability and chaos. And the most humbling thought: if those fluctuations had been just a fraction stronger or weaker, the cosmic web might have looked entirely different, too sparse for stars to ignite, or so dense that everything collapsed into black holes. Our existence hinges on a quantum roll of the dice, frozen into the fabric of reality before atoms even formed. The universe, it seems, has always known how to turn chaos into structure. And those ghostly echoes, they're still shaping everything we see. If the early universe was as chaotic as we think, space should be littered with the remnants of its violent birth, tiny primordial black holes, no larger than atoms but as dense as mountains. These cosmic fossils, theorized to form from density fluctuations in the first seconds after the Big Bang, should outnumber stars by staggering margins. Yet when we look, we find almost nothing. This glaring absence isn't just a minor gap in our models. It's a crisis for theories that once saw these miniature black holes as the perfect dark matter candidates. The math is straightforward. In the seething plasma of the early cosmos, pockets of matter could have collapsed under their own gravity, squeezing into black holes before stars even had a chance to ignite. Some models suggest these primordial specks would span a vast range of sizes, from asteroid mass monsters to pinpricks lighter than a paperclip. But here's the catch: gravitational microlensing surveys, which scan for the telltale warping of starlight caused by invisible objects, have come up nearly empty. Where we expected thousands of these black holes drifting through our galaxy, we've found only a handful, if any. Either our detectors are missing something, or the universe skipped a step in its recipe. One possible explanation lies in inflation's smoothing effect. If space expanded too uniformly in those first moments, it might have ironed out the wild density spikes needed to birth tiny black holes. Think of it like rolling dough pressed too evenly, and no lumps remain to bake into cosmic crumbs. Alternatively, perhaps these black holes evaporated long ago, their masses so small that Hawking radiation would have dissolved them into particles by now. Yet even this has problems. The smallest black holes would vanish fastest, but intermediate ones should still linger. Their absence suggests evaporation alone can't solve the puzzle. Then there's the dark matter dilemma. Primordial black holes were once a darling candidate for the universe's missing mass after all. They're invisible, abundant in theory, and don't require new particles. But the lack of observed microlensing events has all but ruled them out as dark matter's primary ingredient. That leaves physicists scrambling. If not black holes, what else could account for the gravitational glue holding galaxies together? The answer might lie in even stranger possibilities: actions, WIMP, or particles we've yet to imagine. Yet the story isn't over. Some observations still leave wiggle room. A few unexplained gravitational wave signals could hint at primordial black holes hiding in the gaps between stars. Others speculate they might lurk in the hearts of neutron stars, slowly consuming them from within. And if even a fraction of dark matter turns out to be these ancient relics, it would mean the universe played a trick on us, hiding its oldest objects in plain sight. What's fascinating isn't just the mystery, but what it reveals about how little we understand the cosmos's first moments. The absence of primordial black holes isn't an empty silence. It's a cosmic shout that something in our equations is wrong. Whether it's the physics of inflation, the nature of quantum fluctuations, or an entirely new process we've overlooked, one thing is clear: the universe kept receipts from its birth, and we're still learning how to read them. Cosmic strings are the universe's phantom scars, theoretical cracks in spacetime so narrow, yet so unimaginably dense that a single inch could outweigh Mount Everest. These bizarre relics, predicted by grand unified theories, should have formed as the universe cooled from its fiery birth, like cracks forming in ice as water freezes. Their existence would be proof of a profound symmetry-breaking moment when the fundamental forces, gravity, electromagnetism, and the nuclear forces, split apart to shape reality as we know it. Yet despite decades of searching, we've found no direct trace of them. Their absence isn't just a curiosity, it's a crisis for some of our most ambitious attempts to explain how the cosmos works. Imagine space-time not as a smooth fabric but as a mosaic under tension. As the universe expanded and cooled, phase transitions should have left behind defects, regions where the tiles didn't align perfectly. Cosmic strings would be the most stable of these flaws, threads of pure energy thinner than a proton but stretching across galaxies, vibrating like cosmic guitar strings with enough gravitational punch to warp light and time around them. If they exist, they'd be cosmic lighthouses, revealing physics at energy scales trillions of times beyond what particle colliders can reach. The mystery deepens when we consider their predicted effects. These strings should create double images of distant galaxies as their gravity bends light like a funhouse mirror. They might even snap violently, sending ripples through space-time gravitational waves distinct from those made by black holes. Yet after scouring the skies, we've caught no glimpse of these telltale distortions. The European Space Agency's Planck satellite, which mapped the cosmic microwave background with exquisite precision, found no evidence of string-induced wrinkles. Pulsar timing arrays listening for gravitational echoes have heard no whispers of snapping strings. This null result forces a reckoning. Grand unified theories, which attempt to merge all fundamental forces into a single framework, rely on phase transitions that should have birthed cosmic strings. Their absence suggests either these transitions happened differently than we thought, perhaps more smoothly, without defects, or that our theories need a radical overhaul. Some physicists now propose no-string models where symmetries break in gentler ways, like a pane of glass cooling without cracking. Others argue strings might still exist but in forms too subtle or rare to detect yet, hidden in the noise of the cosmos. The stakes go beyond theoretical housekeeping. If cosmic strings are confirmed, they'd offer a window into physics at energies we can't replicate, hinting at how the universe chose its fundamental rules. Their absence, meanwhile, tells us the cosmos might be more elegant or more mysterious than our boldest theories predicted. Either way, their ghostly non-detection is a reminder. The universe owes us neither flaws nor perfection, only the truth, written in a language we're still learning to read. Current models of cosmic destiny paint two starkly different portraits of how everything might end, one suffused with silence, the other with explosive renewal. On one side lies the heat-death scenario, where the universe expands forever into an eternal, lifeless freeze. Galaxies drift apart until their stars burn out, black holes evaporate, and even atomic motion grinds to a halt. Space becomes a graveyard of spent particles where temperatures approach absolute zero and time loses all meaning. It's the ultimate fade to black, a finale devoid of light, structure, or change. Yet there's an eerie beauty to this bleak vision. The heat death isn't sudden or violent, it's the slow unraveling of complexity into uniformity, like ink dispersing in water until no pattern remains. Entropy wins and the cosmos settles into equilibrium, a state physicists call maximum entropy. No energy gradients mean no work can be done, no stars ignited, no life sustained. The universe, in essence, forgets itself, but this isn't the only possible ending. Quantum physics whispers of far stranger conclusions. One hinges on the unsettling idea of vacuum decay, a phenomenon where the fundamental quantum fields underpinning reality suddenly drop to a lower energy state. Picture a soap bubble popping. In an instant, a new, more stable vacuum would expand at light speed, rewriting the laws of physics as it spreads. Atoms might disintegrate, forces vanish, and space itself reconfigure in ways beyond prediction. The shockwave wouldn't just destroy life, it would erase the very framework enabling existence as we know it. Unlike heat death's slow creep, vacuum decay would be over in a cosmic eye blink, leaving no warning, no survivors. Then there's the cyclical rebirth hypothesis, where the universe doesn't end but reinvents itself. Some versions suggest quantum tunneling could spark a new Big Bang from the ashes of the old one, like a phoenix rising from an infinitely dense ember. Others propose that dark energy currently accelerating the universe's expansion might eventually reverse its behavior, pulling everything back into a fiery Big Crunch. In this scenario, the collapse could become the seed for another expansion, birthing a new universe with different physical constants. The most radical theories blend physics with philosophy. If the multiverse exists, our universe's demise might be irrelevant, just one bubble bursting in an infinite foam of realities. Or if consciousness plays a role in quantum mechanics, as some interpretations suggest, the universe's fate could hinge on observers in ways we can't yet fathom. What makes these speculations so compelling isn't just their scale, it's their reminder that finality might be an illusion. The cosmos could be a story with endless sequels, each ending merely the prelude to another beginning. Until we uncover deeper laws governing time, energy, and quantum fields, the universe's last page remains unwritten, and that uncertainty, it's the most thrilling mystery of all. From the cosmic microwave background's eerie cold spot to primordial black holes that refuse to reveal themselves, we've journeyed through 25 astonishing truths that rewrite everything we thought we knew about the universe's origins. The Big Bang might not have been the true beginning, just one chapter in an endless cycle of rebirth. The speed of light itself could have been different in those first moments, and dark matter's ghostly touch may have shaped galaxies in ways we're only beginning to trace. Each discovery peels back another layer, revealing not just answers but deeper questions we hadn't even thought to ask. Consider the cosmic ballet of aligned quasars, spinning in sync across billions of light years. What invisible hand orchestrated that? Or the lithium deficit, a cosmic accounting error that upends our understanding of nucleosynthesis. Even the universe's heat defies expectations, lingering warmth where only cold emptiness should exist. These aren't just oddities, they're clues that our maps of reality are missing entire continents of understanding. The most profound takeaway: the universe is far stranger, far more dynamic than our textbooks dared to suggest. What we call laws of physics might be temporary rules, emergent from processes we've yet to uncover. Every anomaly, phantom energy's apocalyptic potential, the missing primordial black holes, the whispers of extra dimensions hints at a grander narrative still being written. So where does this leave us? Not at the end, but at the threshold. For every mystery solved, a dozen more emerge, glittering like uncharted stars. Maybe you'll be the one to unravel them. Stay curious, keep looking up, and remember, the universe's greatest stories aren't in the answers we've found, but the questions we've yet to voice. If these cosmic enigmas left you hungry for more, you're in the right place. Hit subscribe, and let's keep exploring the unknown together. The next revelation might be just one video away.